That's not the one I want. This is, yeah. So put this down at the bottom. Last time we looked at, ridge, I believe, and we were discussing, one of the issues that came up was, how does it compare to ordinary least squares in terms of prediction? So I did an example. A big piece of what I'm going to do today is to give us some more practice in using ridge and lasso and in setting up the whole thing for prediction and showing how it works. So the 2 points, the 2 takeaways from this is that, well, OOS, ordinary least squares, will always fit the model better than a regularized regression. It typically won't perform as well when you won't go for prediction. And the other thing I want to do is to sort of really spend some time looking at syntax to get these things right. Now, incidentally, this presentation should take under an hour, maybe 45 minutes, I don't know. It took me large multiples of that to get the syntax right. So, and this is always an issue, with computer coding. Much like rebuilding a house, the last 5% of the work takes half the time. So anyway, let's do it. So just to continue the discussion we've had, maybe hopefully summarize it better because I've tried to. Why would you think that regularized regressions will give you better predictions than just ordinary least squares? So, I mean, what you're doing is you're taking, ordinary least squares and saying, I'm not going to let my coefficients get too big. I'm adding this penalty if they get too big. And there's 2 sort of explanations for why I think this is usually true. And the first is by forcing the coefficients to not be too large. You're forcing them from finding the absolute best one typically. So this means that you're not modeling the training data as perfectly as you could. And what this means frequently is that you're not modeling the noise. In other words, it's forcing you to just sort of look at the gross features that are apparent in your data set and ignore very minor, subtle things that a larger coefficient would do. And I'll talk about this a little bit more in a second, but the other major reason is that when you do regularization, it makes the models more robust to small changes in the data. And in particular, it will usually deal much better with highly correlated variables than ordinary regression will. Now, I didn't write this down, but to me, this is an important feature about producing a good model. If we really, we believe that there really is some sort of model or, close to model out there that is going to tell us what we want about the data, then we got to believe that as we sort of move around in the parameter space, we found the right, if we found the right model with the right set of parameters, if you move the data a little bit, you'd expect, what's the best parameters to change just a little bit. And that's what you mean by robustness, that small changes in your data input should really only cause small changes in the model. And these methods are much better with that. So to get a little more technical without doing math, if you have highly correlated variables, for example, what this means is the determinant of the design matrix, when you use this, gosh, I probably should, all right. What it means is that the design matrix is going to have a very small determinant. Now, when you find the coefficients, you need to invert the matrix, and that means you have to invert the determinant. So the inverse of the determinant is going to be really large. And what this means is, you take 1 over a very small number, and that's very large. You change that small number by a very small amount, it makes a very large difference in the value that you get. So, 1 over 100 is, 100, but 1 over 100 plus 1,000, 0.001, it's just, excuse me, 0.001 plus 0.0001 becomes a much different number. So regularization forces the matrix to have larger determinant because when you regularize, you're adding, some multiple, and it forces the determinant to be highly non-singular. So small changes in the data do not lead to big changes. Are there any questions on that?
Yeah, I have one question regarding regularization. because we are giving a bound that a beta has to be within some bound. So probably a lot of times we may end up finding a beta which is not the minimum for the function. Probably when we are looking at the gradient descent, it may stop before convergence.
Absolutely. You would not use gradient descent. I mean, this is you're finding the minimum in an area, and you will not necessarily at all have the derivative equal to 0.
Right.
Yeah, so that's just true.
But it can be far away from the minimum as well.
Right. Well, what I'm saying is, let's say you had a model where you had some very correlation of 0.95 for a few variables.
Right.
That would mean that the determinant was very small. So any noise in your data is going to have a huge difference. Now, when you regularize, you would not be able to make some coefficients really small and others really large. Everything has to be within that bound. Now, in fact, at least for Ridge, you could, in the end, solve a different problem with gradient descent to find the solution. But you are absolutely not finding the optimal solution. That's the whole point. You're finding one that's much less sensitive. By finding a suboptimal solution, you're finding one that's much less sensitive to changes in the data. Did I explain that well enough?
Okay.
I mean, that's, in some sense, that's the whole point, is you don't want the optimal solution. The optimal solution can be very unstable.
Right. Okay, yeah, I see.
Now, at least for Ridge, you may recall, shall I try an experiment? I'm going to turn this over and see if you, tell me if you still see my screen. Do you still see the screen?
I still see the, what are you trying to do, Adam, right now?
I'm trying to, in my move, I lost my pad. I'm just going to keep it there. I can't find, I haven't been able to find, I don't think I lost it. Just haven't found yet the pad I have that would allow me to do writing.
Okay.
I wanted to just show you the fact that, when you do ridge regression with the parameter lambda, you're just finding the design matrix, which has been perturbed by a matrix with lambda on the diagonals. So that
right. That part I remember. That part, right? Yes.
Yeah. For a ridge, you can solve it by that way.
Okay.
Lasso actually has a very simple way of being solved, but it's not. It's an algorithm that's very different.
Okay.
Okay, so you may recall that GlimNet is the package that has Lasso and Ridge, and so this is just a bunch of nonsense about loading it. But then at the very bottom, I'm loading this library ISLR because it contains a data set called hitters, and this command options equals SciPen 999. It just means that I won't be seeing any scientific notation. So, and I always say the first thing you do when you look at a data set is you should look at it. So let's take a look at it. And remember, head and summary are the two things to you. They show you the first few lines and a summary of the statistics. So here we go. The head of hitters shows it's a bunch of names, most of which, or all of which, are not known to any of us. And then the columns are these things: at bats, hits, home runs, et cetera, and finally there is salary, is the important one. New league. I mean, so one of the points I want to make is that at some point domain knowledge can be very useful, but it's particularly useful when you want to go about creating variables. But if you already have a data set which has all the information, domain knowledge is not important. So by this, I wish to say that if you're either bored, uninterested, or unknowledgeable about baseball, that's not relevant. All we know is we have a bunch of people, and we have their salaries, And then we have information, certain statistics about them that we could say the company that hires them thinks are important. And then, so summary just gives us the information. And one thing I always do when I look at summary, it's always very interesting, is it always tells you if there's any NAs or, missing data. We can see it's balanced as the new league, put outs, well, I don't know. But the most interesting thing I take away from this is that there are 59 people for whom there are no salaries. Since the object of this exercise will be to see, can we predict this salary? That means we got to get rid of those to get started. So in R, there's a nice function called complete.cases. It returns a logical index that tells you which rows have no NAs and which ones do. It's true or false. And so we can just use that. So if I'm going to distinguish the two sets by calling them hitters with a small h, and I just say complete case of hitters, comma. So complete case of hitters is going to be return a logical, a row of logical vectors, the same length as hitters, and it's going to be true if it's a complete case, i.e. there's no NA, and false otherwise. So that's how we get rid of it. And oops, this is something I should have mentioned yesterday, and that is, BlimNet is an older package, and sometimes it can be a little fussy with how it wants the data. And there's this model.matrix function that takes a data set, in this case hitters, and it tells it what's the Y variable, and then it creates the other things. And a nice thing about this is, so if you do like using R, this will automatically create the categorical, take categorical variables and create the dummy variables. So it does that very nicely. So I've set it up. I have my X set, my Y, and now let's take a look at what happens. And just remember that there's sort of two parameters that are very important to us: the value lambda, which is the amount of regularization, and there's also this penalty alpha, this parameter alpha, which tells you whether it's telling you whether you're going for ridge or lasso. So just for randomness, I decided to do ridge first. Okay, so just recall what ridge does is it sort of uniformly shrinks the coefficients. It puts them in a round ball, a circular ball. And if your data matrix was nice, in other words, if you set it up so your features are uncorrelated, which means orthonormal, then the shrinkage is by 1 plus lambda. So if your regularization constant is lambda, it shrinks by a factor of 1 plus lambda. Now, to keep life reasonable, the other thing I'm going to do is tell the function what are the lambdas that I wish to look at. So I've created this grid, which goes from 10 to minus 2. So it's just 100 numbers between 10 and minus 2. So now if I look at 10 to the grid, I get numbers between 10 to the 10th and 10 to the minus 2. So those are going to be my values of lambda I'm going to look at. So I'm going to look at lambdas that range from really big numbers to 1/100th, which is very close to no regularization. So then I just say, I call the function BlimNet. And if in R with a function, if you know the order of the parameters, you don't have to say, what the parameters are. So it always wants X first then Y. So this will do it. And I'm just telling it I want the ridge by saying alpha equals 0. And I wanted to create models for these values of lambda. Question? Now, just to give you some feel for these things, I just want to, go through some of the output. So remember, ridge.model is the object created by BlimNet. And our functions create objects. It's an object-oriented language. And so we can see that these numbers get smaller and smaller. And the last one, as promised, is remember, we went to 10 to the minus 2, which is 0.01. So I did that, and it's created coefficients. So for each one of these 100 values of lambda, I have 20 coefficients. And so the first one, remember, corresponds to a lambda that's really, really large. So let's think. So we're penalizing the coefficients by a really large thing. And then the other one is, and then I looked at 100, which is the other extreme. We saw that 100 is the almost no penalty. And so you can see how very different the numbers you get are. So you can see that applying different degrees of regularization is just going to give you very, very different numbers. And that's the only takeaway. And coef is just a function. It gives you the coefficients. And remember, we saw that it gives you 20, you have 100 columns to the 100 different lambdas, and each one has 20 coefficients. So that's good, but that we used all the data. Let's just do train and test. So this is pretty straightforward. I use two notations sort of interchangeably, but probably, so I just create a, so I divided the data into train and test 50-50. Why? No good reason. I'm just trying to illustrate something, and it just happened to be that that's what I did. So I just sampled the data, and with the sample, it doesn't replace things unless you tell it to. And I say the test set is minus train, and so for indexing, that'll just work fine. And then I have y.test, y.train, x.test, and x.train, and it just created them. Okay, so we have the model, but now I just use the training data. I use the same, I'm still looking at Ridge, and I have the same grid. Now, if you want to see what the model is for a specific value of lambda, you can use this predict. So I just want to show you the syntax. So if you do this, you'll get it right. So the first thing you have to feed it is the model you created. S is the lambda, so it's saying lambda equals 4. And they had a reason that doesn't really make sense to me, why they call this parameter lambda and not, why they don't call it lambda, why they call it S, but they do. And new X, that's the new data. I'm just going to give it the old test data. And we can see what I've done here is I've just sort of put side by side the predicted values and the actual values of the salaries. So we can see Alan Ashby was getting 475. We predicted 404, which isn't so bad. Alan Davis were way off the mark. We're almost double. Well, these guys were predicting negative salaries, and nobody plays for negative, so it's not particularly good. But this is the syntax. Now, in real life, your first attempt at things you shouldn't expect to be particularly good. So the main thing is that you now have something in front of you that shows you the syntax, and it's written out correctly. This was all run, and it works. But I said this is not very good, but maybe we want something more quantitative, like mean square error. So one thing I did was I just said, well, what's the mean of the squares of the differences? And that's really large. That's a really large number. It looked like the salaries were about, 400, 500,000. These are hundreds of thousands of dollars, so this is $404,000. And I'm getting an average error of 1,000,003. And that seems to be too large. So what went wrong? So what went wrong is the first quiz. And so I give you 3 choices. The first is nothing, it's just a crappy model. 2, if it's Euclidean distance, don't you need to take square root? I just took the squares. Shouldn't I took in the square root there? And 3, the formula isn't doing what we wanted to do, namely take each term, compare the two, the predicted value and the actual value, square it, add those up, now divide by the number of prediction things you have, and then take the square root. So that's the first quiz, and those are your choices. Just a crappy model, shouldn't there be a square root somewhere, and I didn't do anything particularly well. And that's the 3 choices. Do we want to do the quizzes, or should we just, it's just...
No, we can speak because there's so many few people, we can just say.
Yeah, okay. So anyone care to speculate?
I would say probably 1, the model is not that good.
okay? It is a crappy model, but in addition, I mean, it's worth pointing out, I took the square, so, you know, we're trying to predict dollars. You know, salary was 404, this is 475. If I take squares, not only am I going to accelerate the differences, but I'm also going to be computing in squared dollars, whatever the hell that is. So it is a crappy model. That's not wrong. You should take square roots, but if you look at the formula, isn't really doing exactly what we want it to. So I just wanted to go through this and get it right. So first thing we want to do is we have the predictions and we have the test values. We want to take the square differences, right? So we do that. Then we want to add those all up. I've just added sum. Then we want to divide that by how many cases we have. That's your average. This is like variance, and what we really want is standard deviation to have the same units. So finally, we have to take that, wrap another set of parentheses around that, and take the square root, i.e. raised to the half power. Okay, and now we get something that's, you know, still crappy, but looks plausible, which is that on average, we're off by about $370,000. Okay, so this is how we're going to measure it. And, you know, this is the kind of thing that with the absence of better tools, you just have to do. Okay. So here's a principle. When you're going to do something over and over again, make it a function. I have to be honest with you. I wrote this out wrong, knowing exactly what I wanted to write out. I wrote it out wrong 2 times and only got it right the 3rd time. If you look at the final thing, there's a lot of parentheses there, and one misplaced parentheses that's, you know, key punch wrong is going to be an issue. So if we make this a function, then this can't happen. We check it once and we're done. So I'm going to just create a function, MSE error, and, you know, I'm just calling the variables what we had, just, you know, because it's fine, doesn't matter. And I've just put it in a function, and now when I run it, instead of having to write out that formula, all I'm going to have to do is put in the 2 values I want, and it'll come out. And we see that if I do run this MSE error for this, I do get what I want, which is, in other words, that's the same value as that. So I did cut and paste it in there, right? And now I just have to use this function MSE error. Okay, so just playing around. And this is worth doing, it really is. Let's see what happens if we take lambda equal to really large. That, remember, the largest value was 10 to the 10th. And we're going to do it on the new data and see what happens. And the error is worse. That's not surprising. This really large lambda, it's unlikely to be the correct value. But let's also try with lambda equals 0. Now, I can make this a quiz, but it's also written here. If lambda equals 0, that means the penalty is 0, right? So this is actually ordinary least squares. And so what's the average error here? It's 383. So it's worse than the 369. So we made the model worse and we're predicting better. Okay, so quiz. Is OLS the best predictor so far? I'll point out we had we used S equals 4, we used really large, and then we used the OLS, and we got, so is it or isn't it?
No.
No, it isn't.
No, because it's like 383 instead of 369, yeah.
Yeah, the 369 is slightly better. Yeah. And that was just from this random value we took lambda equal to 4. Okay, so it isn't. So
I'm just wondering, Adam, like if we try to if we try to pick lambda using cross-validation, probably we might get some better value of lambda, which can do better prediction.
You read my mind. Yes. So how do we find the correct value of lambda to use? And I've written it out here in pretty reasonable detail, but let's go through this. So GlimNet has a cross-validation method. So let's recall what cross-validation does. It divides the data, and in fact, in GlimNet, the default is into 10 pieces. So I just said 10 parts. You could declare with a part of the function. In CV, you'll see. Hold on a second. So you see, you could say folds equals 5, but if you don't put it in, it just simply means 10. Okay. So you divide the data into 10 pieces. For each lambda in the grid, you compute a model using 9/10 of the data and that specific lambda, right? So for a given value of lambda, you can find the best solution with that particular line. You predict it on the unused 10th piece, right? And that creates an estimate of how well that lambda works. Now, you get 10 of these things because you can do this with the left out piece being any one of the 10 pieces. So this way, for each lambda, you get 10 estimates. You average those estimates to get a grand estimate or a real average estimate of what the error is for that specific lambda. Okay. Finally, you now have we have at least 100 different values of lambda, so we have 100 different estimates, and then it finds the best one. Now, it actually does better. It doesn't find the best one out of the 100. It then uses grid searcher or something better than that. I don't recall anymore, and it finds an actual best one. So if I use cv.glmnet and I just use my data, tolling and does ridge, you see it'll give us a plot. So these red lines are the MSEs, the estimates of the error, and the arrows, these are confidence intervals. So I think these are the 2 standard deviation confidence intervals. Now, looking at this, we can see the best lambda is somewhere in looks around 6, and we can see that when the lambdas get very large, it gets pretty crappy. Okay, so and if we want to know what it is, this CV. Remember, I just called the object CV.out. It has one of its properties is the minimum lambda. And it said the best lambda is 293, and I was right because you see this is giving you the logs of the lambda, and I said it's about 6, and the log of 293 is 5.68. So that's the best lambda to use.
Hey, Adam, can you just go up a little bit up at the top of the slide? Where you have, cv.glmnet x train y train, right? Okay, by giving alpha equal to 0, it knows that you are doing
ridge.
Okay, fine. Thank you.
So Professor, so the best lambda is the one which had the
lowest average predictive error when it did this cross validation. I'm sorry to cut you off, but I assume I'm just finishing your sentence, right?
Yeah. That's what I wanted to ask. Thank you.
Yeah. So so you can see it found a value that's not on the grid. The value is off the grid. Yuck, yuck, yuck. But it does find the lambda that had the best. Okay. So the chart shows that this MSE seems to be about 100,000, but we checked it was closer to like 300,000-ish. So why is that? Well, the answer is there's 2 choices. One is that's because it's using training data, and the model is trained using the training data, so it's going to fit the training data a whole lot better than it's going to fit new data. So that's basically choice 1. And choice 2 is, that's weird.
That message should be important. We're not getting that.
Sorry?
Yeah, I think it's because we are doing it with training data.
Yes, exactly. And this is an example that shows you, so it shows you that with training data, the model's almost always, let's put it this way. If you have a model and it fits the test data better than the training data, look at everything you did very carefully. There's probably something wrong, because it should not fit as well. You always expect the model to perform worse on these data than on the data. Wow. Statistically tautological. Okay. So let's see how well it does. So now I'd use my predict function to get the date, my estimates, I just use S equals best lambda, and my data is the test data. And now I come out. Now, I will point out this, that it did about the same, slightly worse than the random choice of 4, which actually was completely random. I chose 4 before I knew what was going to happen. But nonetheless, we can ask, does it improve overall OLS? And, I can use, I know what my best lambda is. I just rewrote this. And the OLS prediction of Reg is, I just set the lambda equal to 0. And I can find the MSE errors for both of them and compare them. And you can see that the best error is about $11,000 better than the, is $11,000 better than the OLS. So it is better. It's not a lot better in this case, but it is better. Okay, so that's Ridge. What about Lasso? Well, one thing I'd point out is, having done all this, doing Lasso is mainly cut and paste. Let me find something. We have this alpha equals 0. Basically, every time we had alpha equals 0, we can replace alpha equal 1, and we should get the answers for Lasso. So the other thing I want to point out is that Lasso works differently in terms of how it shrinks the coefficients. So what happens with Lasso is, you take your coefficient beta, you take its absolute value, you subtract off lambda. Remember, lambda is always positive, right? If the result is negative for that lambda, you make the coefficient 0. If the result is positive, that's your new value. You've shrunk it by lambda. And then, but then you put back the sign. So beta was positive, you keep it that. If it was negative, you now make it negative. So you're just sort of arithmetically shrinking all the things. Okay? So that's what Lasso does. And as I said, it's a pretty simple cut and paste. The only difference is I'm calling it this Lasso.model, and I said alpha equal to 1. And again, to find the best value of lambda, I do the exact same thing. I use cv.glmnet on the training data, and I just set alpha equal to 1. And the only thing I'm going to do different is, instead of calling it best lam, I'm going to go with best lam1 to distinguish between the two.
And don't you have to pass the grid to the cv.glmnet package?
No.
So what is the choices of lambda over which it's evaluating? It's the same set of lambda?
I believe so, yeah.
Okay.
That's actually a good point. I never looked that up. I just always assumed that since you've done that, it does use the same values as lambda. It's conceivable that it just takes the range, it expands the, it may not use the same grid values, that it's conceivable that all it's doing is it's finding the best lambda by starting with parameters and seeing if the model is clear. There is a best value. So if it doesn't if it finds a minimum at an edge, it keeps going, extending. That's a great question. I just always assumed it uses the same thing, but now that you ask and I think about it, I think it must do an independent grid search.
But isn't that the grid you define that as a certain set of values, right?
Right.
So it's going to use the same.
That's what I always assume, but
it has to be defined. So I mean, you define the grid to be powers of 10 or something, right?
Yeah, I did.
So it'll use the same. Because that's what
I was thinking, but
that's the name of that variable has been put equal to.
I'm gonna find out.
Yeah. Oh, that must be. I mean, unless it has some default value, which I don't think it does.
Well, I certainly know that if you don't put in grid,
yeah,
it does have a default set.
Oh, okay.
Now, but the difference is, of course, to find the minimum lambda, if you have the default and your minimum value occurs at the edge, it's highly likely that that's not the true minimum value. The lambda has a unique minimum value.
Mm-hmm.
So if it's right at the edge, it probably means if you continue further in that direction, you get it. So it may just use the default set, and if it finds the value in there, it uses that. And if it doesn't, then it extends as its default set of the grid. That's a great question.
You haven't cleared the memory at this stage, have you?
No.
Okay, so it'll have the same value.
I will check. Get back to you. All right, so all I did here was I computed what the MSC error, the mean square error, is when I use the Lasso. And again, you see I use the best lambda, and I use the new data, and then I use the Lasso best predictions and y test, and it came out slightly worse than the Ridge, by about $2,000. So very comparable. The other thing I thought it was worth showing you is you can get the coefficients. So I just created, I said GlimNet, and here I just used for my grid my best value. So this is just going to create this one model with the best lambda, and now I can get its coefficients. And you can see that these dots mean that they're that those are not used in the lambda. So lambda, the best model, has gotten rid of most of the coefficients, and I wasn't going to add them up because I remembered on the next page I'd written them out. So I have 11 non-zero coefficients. Now, that might be a point in favor of using the Lasso over the Ridge. It has similar results, but since it's only using 11 coefficients, it's a much simpler model.
Roy, what are the coefficients? Can we see the ones that were non-zero
Sure.
again? That's interesting.
Bats, hits. What's most interesting to me, as someone who knows a little bit about baseball, this is home runs is important.
So hits and walks, that seems to be the
hits and walks.
Yeah.
Now, incidentally, I
walk a lot, you don't strike out a lot, I guess.
It's hard to walk a lot and strike out a lot. Yeah. I would have thought strikeouts would be something here too, but no.
That's interesting.
And whether you were on a division winner or not was not only was a negative factor, but yeah, and okay, so that's a pretty detailed example of how you could go and out. And as I said, it took me I would say it was an embarrassing long time, except I'm absolutely not embarrassed. I've been doing this often enough to just know that when you have to write these things out and all the details, and you have it happens all day long in my job. You miss a comma here, a dot there, and you spend 2 hours trying to well, not 2 hours, but you spend time trying to figure this out. So if you have any interest in using these things, I've had the experience, you go to the web and somebody does an